Okay, so our notes today are on section 5.1, polynomial functions, and our content objective is to classify polynomials, graph polynomials, and describe their end behavior. Our language objective is to use the correct terminology to describe and classify polynomials and describe their end behavior. We have a lot of vocabulary, so if you want to pause that and write this all down, stopping there, you can do that now. I'm going to go through and talk through each one of these definitions for the moment. So the first key vocabulary word is monomial. So a monomial is a real number, variable, or product of a real number and one or more variables with whole number exponents. Monomial is our first key vocabulary word because monomials build up our polynomials, but we'll get there in a second. So a degree of a monomial is if it's in one variable. So if we only have x, this is true, but if it's x and y, then you can't talk about the degree of a monomial. So the degree of the monomial is the exponent of the variable. So since they have whole number exponents, we know that the exponent of the variable is the degree of the monomial. So if you had something like 3x cubed, the degree of the monomial would be the third power or cubic in that situation. So a polynomial is a monomial or sum of monomials. So it can have x to the fifth, x to the fourth, x to the third. It can have all sorts of monomials added or subtracted together to create one long string called the polynomial. One example is down here. So the degree of a polynomial, again, if it's in one variable, so this only works if there's only one variable. If it has both x and y or a and b, then it no longer applies, is the greatest degree among its monomial terms. So that leads us to standard form, which arranges the terms by degree in descending numerical order. So here I have a variable to the fifth power, and then I go fourth, third, second, first, and no variable. So standard form, as it was with our quadratic functions or our linear functions, it arranges it in descending order or numerical order. So these are the key vocabulary words that we're going to bring up as we start talking about the behaviors of these polynomial functions that we're going to talk about. So a polynomial function, as you may guess, is just a function that or a curve that represents the polynomial or a polynomial. So I've started to make a table here. So the different degree, so the degree of our polynomial again is the highest exponent in that term. So the degree of our polynomial, the degree will tell us the name using the degree. So if it's the degree is 0, we just have a number, it's called a constant. So we've talked about these before. So this could be any just number. In this case, it will just say 5. It could be anything. The number of terms, on the other hand, talks about how many actual monomials are in that polynomial. So in this case, there is only one term. So the name of the number of terms would be a monomial. If we had something to the first power, it would be a linear function. We've learned about those as well. This could be x plus 4, x minus 5, anything where x is to the first power or without an exponent written there. In this case, the number of terms is 2, so this is a binomial. We've talked about binomials a lot in our factoring as well. So it's a linear binomial in this case. Our first one was a constant monomial. If we have something to the second power, it's a quadratic. We've also worked extensively with those. And this could be something like just 3x squared. It could be 3x minus 4, 3x plus 2x, or 3x squared plus 2x minus 6. In this case, this quadratic function only has one term, so it's still a monomial, even though it's a quadratic function. So it's a quadratic monomial. So again, the name using the number of terms is monomial, binomial, trinomial, polynomial, 4 terms, whereas the name using the degree is constant, linear, quadratic, and then we have cubic. And we'll say this case it's 5x cubed minus 4x squared plus 1. The number of terms here, 1, 2, 3 monomials make up that polynomial. So this is a trinomial. So 3 terms, so it's a trinomial, so it's a cubic trinomial. 4 would be a quartic. And we could have something like x to the 4th minus 2. The number of terms here is 2, so it's a binomial. So our example is a quartic binomial. And last but not least, so that we're going to speak about, is a quintic. So we could have something like 2x to the 5th plus 5x cubed plus x minus 2, and there are 1, 2, 3, 4 terms there. So that we'll call a polynomial of 4 terms. So we stop having specific vocabulary word or single words that describe that polynomial. So we just describe it as a polynomial of 4 terms. All right, make sure you write down any questions, comments, concerns on this stuff. I'm going to flip the page for a quick check. So make sure you have this all written down. So our quick check, I want you to classify the following by degree and number of terms. So sort of like we were just doing with that table. So the first one I'll give you is x to the 4th minus 5x cubed plus x minus 1. And the second one I'm going to give you is x cubed minus 1. So try classifying those on your own. I'm going to go over them now. So this one we see is to the 4th power. That's the highest degree here. So we know it's a quartic polynomial. And there are 1, 2, 3, 4 terms. So it's a quartic polynomial of 4 terms. This one, we don't see the highest degree on our variable is 3, so it's going to be a cubic polynomial, and there are only 2 terms, so it's a cubic binomial. So we have a cubic binomial there. All right, so that's what we're going to do for classifying. But why are we talking about these different degrees? What is this going to tell us, and what is this end behavior that was mentioned in our objective? So the next thing I want to talk about is the degree of these polynomials and what they can tell us about the function. So the degree of a function, so again, if it's quartic to the 4th power, cubic, 3rd power, so that degree is going to affect a lot about our graph. So it affects the shape of the graph. It affects the maximum number of turning points, which we also call relative maximums or minimums. And we'll spend more time talking about those first 2 points later in this unit. We're also going to spend more time later talking about the number of roots or solutions. So the degree of a function affects all of these things, as well as our focus for the rest of this lesson, the end behavior. So we'll talk about the shape, the maximum, minimums, the number of roots or solutions, and later on, but today we're focusing on end behavior. And what end behavior is the direction, or directions, I should say, of the graph at the far left and far right. So all of these things are determined by the degree of our function. So I'm going to give you some examples of some polynomial functions, and then we can talk about their end behavior. So the first one I want to show you, we'll start with a quartic function. And I'm not going to spend a lot of time graphing precise points, but it's going to be an approximate model of 4x to the 4th plus 6x cubed minus x. So if I have this graph, I'm not going to spend time with points, as I said, but it would look something like this. So this could be a quartic function or function to the 4th power. The end behavior here as if we look at the end behavior, the far left is this arrow. So as this arrow going on forever goes up, so the end behavior to the left would be up, and to the right would also be up. So our end behavior here is up and up, or forever increasing on both ends of the function. So end behavior again is basically where these arrows are pointing as the function continues on forever. Our second example, I'll do a cubic function. So A cubic function, we'll just do the basic y equals x cubed. And again, not spending too much time with precise points here. If we have, I should at least label. If we have a cubic function, it could look something, or it could look something like that, or it would look something like that. In this case, our end behavior would be, since this one's going down forever in this arrow, it's going to be down and up. So these are opposites in this case. So our end behavior to the left is down, our end behavior to the right is up. I'm going to flip the page for a couple more quick examples and then the rule that we can follow to determine end behavior. So the last two examples, I'm going to give us a quadratic. And we'll do y equals negative x squared plus 2x. And this could look something like this. This is x and y. So again, our end behavior is down and down. The last one I'm going to show you to see if we can sort of decipher the rule together is a cubic function, y equals negative x cubed plus 2x. If I draw this function, do a rough sketch of it, have my y and x axes, it's going to look something more like that. So we have a function that looks more like this. So our end behavior is going to be up and then down. So pretty straightforward, I think. It's just whichever way the arrow is pointing when you look to the far left or far right. But this follows a pattern. And so our key point is going to be the pattern that this follows. So our key point here is if the degree is even, the end behavior is the same on the left and right. So if we look at our even quadratic, it's to the second power, it's down and down. If we looked back at our quartic function, it's up and up, whereas our odd behavior, or our end behavior for odd degreed functions, is going to be opposite directions. So if the degree is odd, the end behavior goes in opposite directions. You may be wondering then, how do you determine if it's going down or up? So if it's even, I know that they'll go either both down or both up, but how do I know if they're going down or up? And same with cubic, I know one's going up, one's going down, but how do I know if the left's going up and the right's going down or vice versa? And then, so these are about even and odd. The other thing to keep in mind is the a value. So if a, which is the leading coefficient, is positive, then the right side goes up. So similarly, I'm not going to write it, but if a were negative, then the right side would go down. So since a is negative here, I know it's going to go down. Since it's even, I know it must be down and down. Here it's negative, but it's odd, so I know they're going to be opposite. The right side's going to be down, which means the left side would have to go up. So you can kind of reason through what these will be based on these two rules. So I want you to do a quick check as our last thing before we go. I want you to determine the end behavior of the following functions. And our first one is f of x equals 3x to the fifth minus 4x squared plus 1. And our second one is negative 2x squared plus 1. Try them both on your own. I'm going to go over them. So this one, I'm going to abbreviate end behavior to EB. It's positive, so I know the right side goes up. And since it's odd, I know they're going to go opposites. So since the right side is up, I know the left side would have to be down. So I kind of worked backwards there. I knew up, so then the other one must be down since it's odd. Here, my end behavior, I know it's negative, so the right side is going to go down. So then, since it's even, they're going to be the same, so it's going to go down and down. So make sure you write down any questions, comments, concerns you have on any of this, and we can go over it together in class.